Hello friends, I welcome you in lecture number 39 on higher order ODEs. In this lecture, we are going to discuss about method of reduction of order. This method is used to obtain second solution if one solution of second order homogeneous differential equation is given, and we have ready-made formula to obtain the second solution of homogeneous second order differential equation if first solution is given. We recall that second order homogeneous linear differential equation can be written in this form: y double dash plus some function of x into y dash plus qx into y equal to 0, where px and qx are functions of x or constant. And suppose we are given one solution of this differential equation, say y1, and using that solution we have to decide the second linearly independent solution. So this method of reduction of order is used in this case, where we are given the value of first solution, and using that first solution we have to determine the second linearly independent solution. So remember that formula of reduction of order: second solution is given by first solution times integral of e to the power minus of integral of px with respect to x. This px is coefficient of y dash after we write our equation in this standard form, and we have to divide by square of first solution. Whatever quantity we obtain, we have to integrate that quantity with respect to x. So using this formula, if we are given one solution, then we can decide the second linearly independent solution. This method will be helpful if we have differential equation with variable coefficients. We are not able to solve every differential equation with variable coefficients. So sometimes if we know one solution, then using that solution we can determine the second linearly independent solution. And we are going to discuss one example related to this method. Sometimes they ask you to determine the second solution if one solution is given. So first step is you write down your equation in this standard form. If it is not given in this form, you first write down your equation in this form: y double dash plus px into y dash plus qx into y equal to 0. And suppose one solution is given and it is denoted by y1, then the second linearly independent solution y2 of equation number 1 is given by y2 equal to y1 times integral of e raised to minus of integral of p with respect to x divided by y1 square integral with respect to x. So we understand this method with the help of this example. We are given that y1 equal to x is one of the solutions of this differential equation, and we are asked to find out second linearly independent solution. So first we write down that y1 is x. It is given that y1 equal to x is solution of equation x square into y double dash plus x into y dash minus y equal to 0, and we denote this by 1. Now this is not in standard form. Standard form for this method is we must express our equation in this form: coefficient of y double dash is 1 plus some function of x into y dash plus qx into y equal to 0. Here coefficient of y double dash is x square, so I have to divide by x square. Whole equation is divided by x square. So here I have x and divided by x square, that is 1 by x and minus 1 by x square y equal to 0. And now we compare this equation with standard form. Comparing this equation with y double dash plus px into y dash plus qx into y equal to 0, we can see that px is coefficient of y dash, which is 1 by x here. So px is 1 by x. In our formula we require px only and y1 is x. So now we can use the formula. We can find out the second solution. The second solution of given equation 1 is y2 equal to y1 times, remember this formula, integral of e raised to minus integral of function p with respect to x divided by square of first solution integral with respect to x. First solution is y1 equal to x. So here I write y1 equal to x. Here also I will divide by y1 square, that is x square. P of x is 1 by x, so I integrate here e to the power minus integral of 1 by x, and whatever I obtain here, that again I have to integrate with respect to x, and this is equal to x times integral of here x square e raised to minus integral of 1 by x is log x divided by x square integral with respect to x. This I have replaced by log x. Integral of 1 by x is log x. This is equal to x times here x square as it is. This I can rewrite as e to the power ln x raised to minus 1 integral with respect to x. Here we have used the property of logarithm. If I have n times log m, then I can rewrite it as log of m raised to n. Here I have minus 1 in the product, so that I have taken in the power of x. And we know that if we have e raised to ln alpha, then we obtain alpha, because these two functions are inverses of each other. So this is equal to x, and this is x to the power minus 1 x square integral with respect to x. And again I can take 1 by x square can be written as x to the power minus 2 integral with respect to x. This I can again rewrite as x to the power minus 1 minus 2, that is x to the power minus 3. Integral of x to the power minus 3 is x to the power minus 3 plus 1, that is minus 2 divided by minus 2. And finally I will have x divided by x square, that is minus 1 divided by x. And therefore the second solution is y2 equal to minus 1 divided by x, and first solution was y1 equal to x. So in this way you can easily obtain the second solution if one solution is given. And if you observe, this is Cauchy-Euler equation, so you can solve this Cauchy-Euler equation and you will find that your solutions are y1 equal to x and y2 equal to 1 by x minus 1 by x. But if they have given one solution and they ask you to find out the second solution, then you should use this method of reduction of order. And you have to just remember this formula. Suppose you are given one solution, say y1, then second solution is given by y2 equal to y1 times integral of e to the power minus integral of p of x dx, this whole quantity divided by square of first solution integral with respect to x. And this px is coefficient of y dash in the differential equation y double dash plus py dash plus qy equal to 0. And this method is for second order homogeneous linear differential equation, and coefficients can be variable also, no problem. If y1 is given, use this formula to obtain the second solution. So in this lecture I wanted to introduce this method of reduction of order, and this method will be used in the topic of series solutions of ordinary differential equations. We will require this method of reduction of order in this topic when we will discuss homogeneous method. And this is all about this session. I hope you like it. Thanks for watching.